Hello, my name is Nathan Farmer and welcome to my presentation on our fourth lab, Circuits and Capacitors. So in this lab, essentially the purpose of it was just to predict how different circuits would react in particular situations. So first we would examine a particular circuit, make some predictions, and then we would test that to a computational model. And then finally, towards the end of this, we actually graphically calculate a time constant of an RC circuit. So some things that we had to keep in mind were just voltage and how to calculate it for different parts of a circuit, and then particularly Ohm's law, relating current, resistance, and voltage all to each other throughout the lab, and then Kirchhoff's laws, obviously very important. Knowing the node rule that the current in and out of a node has to be equal, and then through a loop, all of the voltages must add up to be zero. So in the first part of our experiment, when we weren't working with capacitors, what they had us do was look at the current through these 2 points on this circuit in the top right. And as we try to solve this, the first things we have to do is look at the resistors in series, make them equal to just one resistor, and then use Ohm's law to calculate the current, which is just V over R from the batteries 1.5 plus 1.5 over the resistance to get 0.0204 amps, which is very close to the measured value in our calculation in the bottom right. So immediately after this, what they had us do was to reverse the current through the ammeter and see if this actually makes a difference. And as we can see, it had no change in the sign, which means that these ammeters actually were just measuring the magnitude of the current. Additionally, another thing it had us do was to replace one of these ammeters with a voltmeter and see what happens to the other ammeter. As we know, these voltmeters have infinite resistance, and as such, there's no current actually able to flow through this circuit. So the ammeter reads 0 and the voltmeter reads 3 volts. Additionally, another thing it had us do was measure the voltage between the different components in this circuit. And as we know by the loop rule, these should all add up to be 0. And as we can see through this graph, that's exactly what happens, stepping up with the battery here and then stepping back down with the resistors down to 0. One important thing to note here is that when we use this voltage and current that we've calculated or that we've measured, it doesn't actually quite add up to the actual resistance in the circuit as a result of the tools not being quite accurate enough. And then the final thing we did in the non-capacitor section was we measured the voltage across a resistor with a voltmeter, and then compared this to an ammeter in parallel. So both of these are actually in parallel, but the difference here is that the voltmeter has infinite resistance, whereas this wire and ammeter have 0 resistance. So this means that all of the current is going to flow through the ammeter and none of it's going to flow through the voltmeter. So the voltmeter has no impact on the circuit's or on the current of the circuit, but this ammeter has completely changes the way the current flows. So in the second part of our experiment, when we work with capacitors, what we can see here is that at first what they had us do was just charge and discharge a capacitor through a light bulb and see how it starts bright and gets dimmer, and then notice how as long as it's flowing through the same resistance in the circuit, it's going to take the same time. And then the final thing we had to do was to calculate the time constant of this circuit. And then, as we know theoretically, this should just be 0.02 farads times 30 ohms to be 6 faradohms. But for us to calculate this ourselves graphically, what we needed to do was take the this equation delta V equals delta V naught times e to the power of negative time over the time constant, arrange it so that we can get the time constant to be the slope of this function where y is ln of delta V over delta V naught and x is just time. And when we do that, we get the slope equal to -1 over the time constant, and then calculate it out to be 6.001, which is obviously very close to what we calculated theoretically earlier. And this is just some final afterthoughts. What if we did this lab in real life and used an actual ammeter? Well, in real life, it's not going to have 0 resistance, and so we have to keep this in mind when we're measuring with them, as that it will act as a resistor in the circuit, and actually reduce the current through it. And then what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, and then comparing this to an ideal model? Well, we know in an ideal model that it should charge instantly, but we know that this wouldn't actually happen in real life, as the wires are going to provide a small amount of resistance. Thank you very much for watching my presentation, and that is all.